So this is lecture 21, and we're studying homomorphisms of groups. So what's a homomorphism? So suppose you have two groups, G and H, and a function phi from G to H. So G and H are groups, and we have a function. And this function is a homomorphism if for any two elements of G, so phi is a homomorphism if for all elements G1 and G2 in G, we have the following picture. G is a group, so I can take these two elements and multiply them together, and that's another element in the group. And phi of that is an element in H. On the other hand, I could also take G1 in G and apply phi to that. I get phi of G1, which is an element in H. And I can take G2 and apply phi to that, and that gives me an element in H. And I can multiply them in H. And G is a homomorphism if these are equal for all G1 and G2. So this is a kind of very beautiful, very simple, but fundamental property that a function might have. And these are the functions that arise in some sense very naturally in group theory. So we look at homomorphisms. And homomorphisms have many properties that it's important to know and to know how to prove. And I proved some of them on Monday. Let me just review some of them. So this was proposition 2.410. We have groups G, H, and K. And suppose we have a homomorphism phi from G to H and a homomorphism psi from H to K. So then we have a composite, G composed with phi from H to K. And the proposition says that if phi and psi are homomorphisms, then the composite function psi phi is a homomorphism. Proposition 2.411 says that if EG is the identity in G and EH is the identity in H, again, I'm assuming phi from G to H is a homomorphism, then a homomorphism always maps the identity to the identity. So phi applied to the identity in the group G is always the identity in the group H. And for all G in the group G, if I take phi of G inverse, that's an element in H. Or I could take phi of G in H and take the inverse of that, and those are always the same element. So phi of G inverse is the inverse of phi of G. Again, these are basic properties of homomorphisms. Proposition 2.412 said that if, again, phi from G to H is a homomorphism, if A contained in G is a subgroup, so if A is a subgroup of G, then phi of A is a subgroup of H. So you take a subgroup of G and look at the image of that under the map phi, that gives you a subgroup of H. And conversely, if B contained in H is a subgroup, then phi inverse of B, that's all the elements of A that get mapped into B, is a subgroup of G. So these three propositions are basic, and the proofs are in the notes from Monday, and of course they're in the text. Any questions about this, or how to prove any of these things? Again, you need to spend a lot of time understanding the proofs line by line and, in fact, word for word. Now, suppose we have a group G and a subset N contained in G. So N is a subgroup of G, really, if it's just a group all by itself. So if the identity is in N, and whenever G1, G2 are in N, then the G1, G2 is in N, and G1 inverse is in N. So a subset of a group that contains the identity and is closed under the two group operations of multiplication and taking inverses is a subgroup. So for example, this is really a very simple example. 2z, which is the set of even integers, is a subgroup of the additive group Z. The identity 0 is even, and the sum and difference of even numbers is even. So this is a simple example, maybe the simplest example of a subgroup. Of course, for any group G, we have G is a subset of itself. So G is a subgroup of G. And if I take the identity element, that's a subset of G, is also a subgroup, because this contains the identity and closed under multiplication and inverses. So every group contains these two trivial subgroups, the whole group and just the identity, but groups often contain more subgroups. Now, there's a very curious special property of a group that's important. So a subgroup N of a group G is called normal. So this is really a critical definition. I mean, you have to have this memorized if you like. You have to know what it is. If I ask you on a test to define a normal subgroup, you have to be able to do it. And it's really just one line. So a subgroup N of a group G is normal if for every element G in the group G, and for all elements N in the subgroup N, we have G N G inverse is in the subgroup. So if you take the subgroup N, if you take an element of that subgroup N, and then for every element of the group, G and G inverse is in N, then that's what's called a normal subgroup. An equivalent way to write that is that G capital N G inverse is contained in N. This means the set of all elements of the form G N G inverse for all N in the subgroup N. So, but this is the definition. Right? A normal subgroup. It's extremely important in algebra. And there's a normal subgroup associated with every homomorphism in the following way. So let phi from G to H be a homomorphism. What is called the kernel of phi is the inverse image of the identity in H. So this means the set of all G in the group G such that phi of G equals the identity. So it's always good drawing pictures. Here's the group G, here's the group H, and you have this function phi from G to H. And in each of these groups, you have an identity element. It's usually labeled E, but because I have two groups, I'm going to give subscripts. EG is the identity in G, and EH is the identity in H. And we already know that phi applied to the identity in G is the identity in H. So if we look at the set of all elements that get mapped to E sub H, that includes this E sub G. So in here, we have some set K. These are all the elements of G which phi maps to this one single element H. So homomorphism is not necessarily one-to-one. Homomorphism is not necessarily one-to-one. So you can have many different elements that get mapped to E sub H. But we know there's always at least one, namely the identity in G. So this set of elements is called the kernel of phi. Let's look at a very simple example. Suppose we take G to be the integers and H to be the integers mod 2. That is the set of cosets 2z and 1 plus 2z. This is the even numbers. This is the odd numbers. So this forms a group, and we have a function phi from G to H defined by phi of an integer n is n plus 2z. And this is a homomorphism. And the kernel of phi, it's phi inverse of the identity, which is 2z. And that's just the even numbers. Every even number gets mapped to the set of even numbers. In this map, sorry, let me just write it like this. This is z, and this is z2. So every integer, n, gets mapped to n plus 2z. So if n is even, this is just 2z. If n is odd, this is 1 plus 2z. The identity element in this group is the set of even numbers. So the kernel of phi is, in fact, the set of even numbers, which is a subgroup. Let me add one more remark. So recall, a group G is abelian if xy equals yx for all x and y in the group. So that n be a subgroup of G. For every element n in the subgroup and G in the group, what is this element that was sometimes called the conjugate? G and G inverse. Because the group is abelian, I can write this as Gn is the same as Ng, G inverse. And G times G inverse is the identity, and N times the identity is N. So G and G inverse is equal to n for every element of the subgroup and every element of the group. So in an abelian group, every subgroup of an abelian group is normal. So the interesting thing is for groups that are not abelian, which are also typically the most interesting groups. So for an abelian group, if you want to know if a subgroup is normal, you don't have to do anything. The answer is immediately yes. If the group is abelian, every subgroup is normal, but non-abelian groups are very different. But there's one way to always know we have a kernel, a normal subgroup, and that's the following, which is in proposition 2.415. So phi from G to H is a homomorphism of groups. Then the kernel of phi, which we write as kernel, K-E-R of phi, that's my notation, is normal, is a normal subgroup of G. And how would we prove this? Proof. So suppose we let K be the kernel of phi. So what do I have to say about this? I want to prove it's a normal subgroup. So first, I should prove that it's a subgroup. So the kernel of phi, this is all elements X in the group such that phi of X is the identity in H, right? So again, we always have the same picture. Here's the identity in H. Here's the identity in G. I have this map phi. And here I have all the elements of G that phi maps to the identity. So we already know that phi of the identity of G is the identity in H. So the identity in G is in this set K. If X and Y are in K, so I want to show that K is closed under multiplication, then phi of X is the identity and phi of Y is the identity. But this implies that if I take phi of X times Y, because phi is a homomorphism, this is phi of X times phi of Y. That's the identity times the identity, which is the identity, which means XY, the product, is in K. So K is closed under multiplication. Right. Just, excuse me one second. So this set K is closed under multiplication. What about taking inverses? Well, phi of X inverse, we proved that if phi is a homomorphism, this is the inverse of phi of X. But phi of X is in the kernel, so phi of X is the identity, and the inverse of an identity is the identity. So X inverse also gets sent to EH. So X inverse is in K. So all this says that proves that K is a subgroup. And why is it normal? So suppose X is in this kernel and G is any element in the group. So then what can we say? Phi of GX G inverse because phi is a homomorphism, this is phi of G, phi of X, phi of G inverse. But phi of X is the identity. So this is phi of G, the identity, and phi of G inverse is the inverse of phi of G. So the identity, cross it off, because the phi of G times the identity is just the identity, is just phi of G. And phi of G times phi of G inverse is the identity. So Gx G inverse is in K because of this. So that is a proof that the kernel of a homomorphism is always a normal subgroup. Okay. Again, you really need to spend a lot of time working through the details of this proof, because the reasoning is central to understanding some algebra. Okay. Any questions? Recall that in general, if you have any function from a set G to a set H, this is called one-to-one, or a synonym is injective. If two different elements in G gets into two different elements in H, or equivalently, if phi of G1 equals phi of G2, if and only if G1 equals G2 for all G1, G2 in the group. So again, the picture is here's G, here's H, here's your function phi. If you take elements G1 and G2, which are different, they get mapped. So if these are different, here's phi of G1, here's phi of G2, and these guys will be different. So different elements in G get mapped to different elements in H. Not every function has that property, of course. But a function that does have that property is called one-to-one or injective. And proposition 2.416 says a homomorphism from G to H is injective if and only if the kernel of phi is just the identity. So we know the kernel of phi is a subgroup of G, so it has to contain the identity. But if the only element in the kernel is the identity, then phi is injective and conversely. So the proof, we can do it in two steps. If phi is injective, and because phi of the identity in G is the identity in H, then no other element can be mapped to the identity in H. So the kernel of phi is just the identity in G. So if the map is injective, the kernel is the identity. Let's prove the converse. Suppose the kernel of phi is just the identity in G. We must show phi is one-to-one. Well, let G1, G2 be in G, and H be in H. So if phi of G1 and phi of G2 are both equal to H, what can we say? Then let's take phi of G1, G2 inverse, this element. So this is phi of G1, phi of G2 inverse. That's phi of G1 phi of G2 inverse. This is because phi is a homomorphism, and this is because phi of the inverse of an element is the inverse of phi of the element. But phi of G1 is equal to H. And phi of G2 is H, so this is H inverse. And H times H inverse is the identity. So G1, G2 inverse gets mapped to the identity. So G1, G2 inverse is in the kernel of phi. But our hypothesis is that the kernel of phi consists only of the identity, which means G1, G2 inverse is the identity, which means that G1 equals G2. So being one-to-one or injective is equivalent to having the kernel equal to the identity. Let's look at a nice example. Since Math 313 is a prerequisite for Math 314, you've taken linear algebra, but even in pre-calculus sometimes, we can look at 2x2 matrices, A, B, C, D, and you learn how to add, subtract, and multiply matrices. And so here's a matrix A, and we define the determinant of A to be AD minus BC. So one thing that you learn is if the determinant of A is not 0, then there's an inverse matrix, A inverse, which is 1 over the determinant of A times the matrix, I think D minus B minus CA will work. And you can check that A times A inverse and A inverse times A is the identity matrix 1, 0, 0, 1. So the set of 2x2 matrices with non-zero determinant is a group, which is usually written GL2R. So 2 means we have two, so GL, L means linear, like matrices come up in linear algebra. We're looking at 2x2 matrices with real numbers as the coefficients. G stands for general. This general linear group is the multiplicative group of invertible 2x2 matrices. That's the same as the multiplicative group of all matrices with non-zero determinant. And again, in linear algebra or high school algebra, depending where you went to school, there's a simple fact about determinants, which says the determinant of the product of two matrices is the product of the determinants. This is a little bit complicated to prove for n by n matrices, n by n numbers vertically and horizontally, but for 2 by 2, you can just prove it by just writing down two matrices and multiplying out, checking this formula directly. So what this says is we have two groups that we can consider, GL2R. So this is the group of all matrices, 2 by 2 matrices with real coefficients and non-zero determinant. And we also have, this is the non-zero real numbers, another multiplicative group. And there's a function, the determinant, which sends every matrix to its determinant. Right? So this is the ABCD gets mapped to the number AD minus BC. And this, because of this property, this is a group homomorphism. And this is the multiplicative group of real numbers. And what is the identity? It's just the number 1, right? 1 is the identity. 1 times 7 is 7. 1 is the identity in this multiplicative group. So what is the kernel of this homomorphism? The kernel of the determinant is all matrices A, B, C, D, such that the determinant, which is AD minus BC, equals 1. So the kernel of this map is all 2 by 2 matrices with determinant 1, and that is usually denoted SL2R, which is called the special linear group. It's special because it's just the matrices of determinant 1. And by our theorem, our proposition we just proved, the special linear group SL2R is a normal subgroup of GL2R. Right? That's a very, very, very useful fact. Okay. And there are lots of matrices with determinant 1. So, for example, if I take the matrix 7, 4, 5, 3, the determinant of A is 7 times 3 minus 4 times 5. 21 minus 20 is 1. So this is an SL2R. If I take the matrix B equal 7, 4, 4, make up something, 3. The determinant of B is 7 times 3 minus 4 times 4. That's 21 minus 16, that is 5, which is not 0. So B is in GL2R. It's a matrix with non-zero determinant, but B is not in SL2R. So this is a matrix in GL2R. This is a matrix in GL2R, but this matrix is also in SL2R. Let's look at another example, a nice, very nice example. Suppose let G be a group, A an element of G. So we say that A has order n if n is equal to or greater than 1, and A to the n is the identity, and n is the smallest integer with this property. So an element of a group has order n if for some positive integer n, A to the n is the identity and n is the smallest number with that property. And we say A has order infinity if A to the n is never equal to the identity for all integers n greater than or equal to 1. So in groups, some elements have finite order, some elements have infinite order. Let's just look at an example. Suppose I take G to be the set of permutations on 1, 2, 3, 4, and I take A, let's say, to be the 3 cycle 1, 2, 4. So that's A. What is a squared? You know, 1 goes to 4, 4 goes to 2, 2 goes to 1. What is a cubed? 1 goes to 2 to 4 back to 1, 2 goes to 4, 1 back to 2, 4 goes to 1 to 2 back to 4. A cubed is the identity. So in the symmetric group S4, this permutation, A, is order 3. 3 is the smallest power of A, which gives you the identity. Suppose I take G to be the multiplicative group of non-zero numbers, and I take A to be equal to 2. So A to the first power is 2, A squared is 4, A cubed is 8, A to the fourth is 16. These numbers just get bigger and bigger and bigger. A to the n is never equal to 1 for all n greater than or equal to 1. So A equal 2, this has infinite order in this group. Right? So this is a simple example of an element of finite order 3. This is a simple example of an element in a group of infinite order. Now, here's a nice example of a group homomorphism. So that A be an element of a group G, and I want to define a function phi from the integers into G by phi of k is a to the power k. So I take any integer k, positive, negative, 0. Phi of k is a to the power k. And this is a homomorphism. Phi of k plus L is a to the k plus L. But a to the k plus L is a to the k, a to the L. And a to the k is phi of k, and a to the L is phi of L. So if I take k and L and I add them in Z and then apply phi, that's exactly the same as sending k to G, L to G, and multiplying in G. So this is, phi is a homomorphism. What is the kernel of phi? This is set of all n such that phi of n is the identity. That's the set of all n. What is phi of n? It's a to the power n equals the identity. Well, what are the possibilities? If A has infinite order, a to the n is not the identity for any positive integer n, and not for any negative integer n. Of course, a to the 0 is the identity. This is just 0. So if the element A has infinite order, the kernel of this map is just the trivial subgroup 0. But if A has order k, then for all n, we can write, just use the division algorithm. By the division algorithm, n is kq plus a remainder. The remainder is between 0 and k minus 1. So phi of n is phi of kq plus r, or a to the kq plus r. That's a to the kq times a to the r. This is a to the k to the q, but a to the k is the identity because a has order k. So this is e to the q times a to the r. The identity multiplied by itself is always the identity. This is just a to the r. And r is between 0 and k minus 1. The smallest positive integer for which a to the r is the identity is k. So if r is between 1 and k minus 1, this is not the identity. This equals the identity if and only if r is 0. So n is in the kernel of phi if and only if n is kq plus r, but r is 0, if and only if n is kq for some q. So the kernel of phi is just a set of all multiples of k. It's k times z. Okay. Any questions about this? All right. What else can we say? Let's see. I guess there are more examples I could give, but it's better to introduce the general theory and then look at examples in the context of this more general theory. So I want to now look at section 2.5, which is what are called cosets of a group. And Lagrange's theorem. So suppose we have a group G, a subgroup H of G, and an element G in the big group capital G. So we define what is called the left coset, little g times H. This means this is a set of all elements of the form G times H, where H runs through all the elements of H. And we define the right coset, HG, to be all elements H times G, where H is in H. Now, if the group is abelian, GH equals HG, and these two sets are the same. But if the group is not abelian, these two sets will be different. So let's look at some examples. Suppose I take G to be the integers and H to be the even integers, 2H. So what are the cosets? This is an abelian group, right? G is abelian. So the left and the right cosets will be the same, but what are they? So let's look at some examples. And because this is an additive group, instead of times here, we would write G plus H, say, or H plus G, right? Because if the group operation is addition and not multiplication. So what is, for example, 0 plus h? This is the left coset of 0. This is 0 plus h for all elements in h. That's just h. What is 2 plus h? That's all elements of the form 2 plus h for h and h. H is the set of even integers. I can write this as all elements of the form 2 plus 2k for any integer k, which is the same as 2 times 1 plus k for any integer k. But as k runs through all the integers, so does 1 plus k. So this is the same as 2 plus k. Sorry, this is the same as 2k for all k and z, which is just 2z or h. And in fact, if n is even, n plus h is a set of, let me write it, say 2n. If 2n is even, 2n plus h, this is the set of all numbers which are this even number plus any other even number. That's the set of all even numbers still. And if you have an odd number, 2n plus 1 plus h, what is that? Well, this is a set of everything you can write as 2n plus 1 plus an even integer for any k. If you like, I can write this as 2 times n plus k plus 1 for all k. But n is fixed. As k runs through the integers, so does n plus k. So this is really just 2n plus 1. Sorry, 2k plus 1 for all k, which is just 1 plus h, 1 plus the even integers. So for every odd number, the left coset or the right coset, the odd plus h is 1 plus h. For every even number, the right or left coset is h. Now, if this is probably the first time you've seen cosets, and it can be perhaps a little bit confusing. And the point is, or the thing is, that you have to spend enough time looking at examples and thinking about the concepts so that it moves from being confusing to reasonable to completely obvious. And then maybe you've understood it a little bit better. Let's look at another example. Suppose I take the symmetric group S3, which consists of 6 elements: the identity, the 3-cycle 1, 2, 3, and the 3-cycle 1, 3, 2, and the transpositions 1, 2, 1, 3, and 2, 3. So this group, by now, you have to know thoroughly, because we've used it all the time as an example. What is the what are the cosets, or what's an example? Let's take a subgroup H. So this is my group G, and I take a subgroup H. Say I just take the 2-element subgroup E and the transposition 1, 2. So let's look at a left coset. Suppose I let, for example, G be 1, 3. So what is the left coset GH? I take every element in H and multiply it on the left by G. So that's G times E, G times 1, 2. G is 1, 3. So this is 1, 3 times the identity, which is just 1, 3, and 1, 3 times 1, 2. So this is the transposition 1, 3. And what is 1, 3 times 1, 2? 1 goes to 2, 2 goes to 1, goes to 3, 3 goes to 3, goes back to 1. So 1, 3 times the subgroup is this left coset. What is the right coset? H times 1, 3. So I multiply every element of my subgroup H on the right by 1, 3. So that's E times 1, 3, and 1, 2 times 1, 3. So E times 1, 3 is just 1, 3. What is this permutation? 1 goes to 3, goes to 3. 3 goes to 1, goes to 2. 2 goes to back to 1. So this is the left coset, this is the right coset. And you notice these are different sets, right? So the left coset is not equal to the right coset. The left coset contains 1, 2, 3, but not 1, 3, 2. The right coset contains 1, 3, 2, but not 1, 2, 3. Right? So I would say let's pause for a second and take a look at this and go through the calculation and ask me if you have any questions. You should be able to repeat the calculation, just even copying it down on a piece of paper, but make sure you understand step by step what's going on. So we have the following picture. We have a group G with a subgroup H, that A, B, and G. So here we have G, here we have an element H, and if we look at the coset AH, which is A times H for all H in H, in particular, E is in H, the identity. Every subgroup contains the identity. So AE or A is in this left coset. And if this is the left coset, this is AH. It contains the element A. If you take another element B in G, so B is certainly in the left coset defined by B. And let's say maybe this is, that's the left coset BH. And what we're going to show is that these left cosets are either disjoint, they either have no element in common or they have to be equal. So what we're going to see is that if you have a group G, it's actually partitioned into cosets, A1H, A2H, A3H, and so forth. And every element of the group is in one and only one left coset. Right? So there's a way to partition a group into left cosets, and similarly for right cosets. Also, I should note that because E is in H, then EH equals H. So the subgroup itself, H, is a coset. It's just the left coset of the identity. So I'm going to prove now a number of properties of cosets. So this is proposition 2.5.3. So we have H, a subgroup of a group G, and elements A and B in G. So TFAE, which is an abbreviation for the following, are equivalent. If one is true, they're all true. So the first statement is the element A is in the left coset BH. Second statement is the element B is in the left coset AH. The third statement is that, in fact, these two cosets are the same. The fourth statement is that B inverse A is in H. And the fifth statement is that A inverse B is in H. Proofs. So suppose A is in BH. What does that mean? Then there exists, backwards E means there exists, an element H in the subgroup H such that A is equal to B times H. But if A equals BH, then AH inverse is BHH inverse, which is BHH inverse, which is B times the identity is B. And because H is a subgroup, H inverse is in H. So that means that B is in the left coset AH. So if A is in BH, then B is in AH. So this, therefore, A implies B. That's what I'm proving. That's what I just proved. Why does B imply C? So suppose we have an element A, let's see, in BH. That means A is equal to B times H for some H and H. That means that for all that say H prime and H, AH prime, A was equal to BH, so that's BH H prime, which is B times HH prime, but HH prime is in H because H is closed under multiplication. So this is in BH. So so every element in the left coset of A is in BH. So AH is contained in BH. Because everything in the left coset AH is of the form AH prime for some H prime and H. And I could reverse the argument just as well. If A is in BH, B is in AH. Similarly, B in AH implies B equals AH for some H in the subgroup H. So BH prime is AH prime, but this is in AH because HH prime is a product of two elements of the subgroup H, so it belongs to the subgroup H. So BH, the subgroup, the coset BH, is contained in AH. So if you have two sets and each is contained in the other, then they're equal. So if B is in AH, then A is in BH, and we get AH is contained in BH, BH is contained in AH, so they're equal. So Let me just draw a picture to sort of emphasize what this means. Here's my group G. Suppose I have a coset AH, and suppose I have a coset BH, and there's some element C in both of them. So C is in BH, which means C is B times H for some H in H, which means B is CH inverse. That's certainly true. So if C is in BH, then B is something of the form CH inverse. Let's see, I want to say this slightly differently. Let me do this again. Let me just do it slightly better. So suppose there's an element C, which is in the intersection of these two left cosets, AH intersect BH. So C is AH1 for some H1 in H, and because C is in the left coset AH, and C is also in BH equals BH2 for some H2 in H. So therefore, AH1 equals C equals BH2. So A, if I multiply by H1 inverse, is BH2 H1 inverse, is in BH. So A is in BH, which means, that's what we just proved, AH equals BH. So when we're looking at our cosets, they have to be pairwise disjoint. If two cosets intersect, they are in fact exactly the same. And the two other properties in that proposition are straightforward to prove. So suppose AH equals BH. We want to prove that C implies D, must prove B inverse A is in H. But AH so A is in AH, which is BH. So A is equal to B times H for some H in H. If the left coset AH equals the left coset BH, A, which is A times the identity, is in the left coset AH, which is BH. So A has to be some multiple of B times H for some H in H. So if I multiply by B inverse A is B inverse BH, which is B inverse BH, which is the identity times H, which is H is in H. So B inverse A is in H. So this is the proof that C implies D. And why does D imply E? Well, B inverse A in H implies that the inverse of B inverse A is in H, because subgroup H is closed under taking inverses. And the inverse of B inverse A is A inverse B. So A inverse B is in H. And the last step is to prove that we've come full circle, that E implies statement A. So we want to show A inverse B in H implies A is in BH. But this should be pretty simple by now because let me just reverse this slightly. A inverse B in H implies B inverse A is in H, which means B inverse A is some element H in H, which means if I multiply by B, A is equal to BH, is in the left coset BH. So if A inverse B is in H, then A is in BH. That's what we needed to prove. So that is the proof of the 5 statements in Prop 2.5.3. And Prop 2.5.4, I already just proved. So we have H, a subgroup of G, that A and B be in H. So either the left coset of A and the left coset of B are equal, or these two left cosets have nothing in common. The intersection is the empty set. That's what I just proved. And the second statement is AH is always not empty because A, which is A times E, is in AH. So every left coset is not empty. And G is the union of left cosets, because one of the left cosets, take an element A, one left coset is AH, and AH contains A. So every element of the group is in a left coset. That's what this says. G is the union of its left cosets. Every left coset is a subset of the group. And maybe I will conclude with what is certainly the most important theorem in group theory in this class, which is a theorem of the French mathematician Jean-Louis Lagrange. So I need one very preliminary result. 14. So this is proposition 2.5.5. A, B are elements of a group G. H is a subgroup of G. I have the left coset AH and the left coset BH. And I define a function, I'll call it F, define a function F from AH to BH by F of AX is equal to BX. Sorry, that is a good function, but that's not the one. I'm going to follow the text, though. I do something slightly different. Let me change it. I mean, I prefer my way, but let me follow the text. So define a function F from the group to itself by F of X is B A inverse X. So here's the group G, take an element X, move it to BA inverse X. You're just multiplying X on the left by BA inverse. So this is F is a bijection, 1 to 1 and onto, with inverse function, G from G to G, defined by G of X is a B inverse X. So notice if I take G composed with F of X, that's G of F of X, that's G of, what is F of X? BA inverse X. What is G of that? AB inverse of BA inverse X. The B's cancel, the A's cancel, you just get X. And in the same way, F composed with G of X is F of G of X. That's F of AB inverse X. What is F of that? BA inverse times AB inverse X. Again, the A's cancel, the B's cancel, you get X. So this is a function from this group to itself, which has an inverse. It's a bijection. And if you apply F to the coset AH, so that H, B, and H, F of AH is equal to BA inverse times AH. The A's cancel, that's equal to BH. So F restricted to the left coset AH sends AH to BH. We know it's 1 to 1, and it's also onto. F of AH is BH. So the size, the cardinality of these left cosets is exactly the same. So all left cosets of H have the same cardinality, which means the same number of elements. So I can now prove in front of your very eyes what is definitely a question on the final exam, Lagrange's theorem. Lagrange's theorem says the following: G is a finite group, H is subgroup. Finite is important, right? It's not an infinite group, it's a finite set. The cardinality of H is the number of elements in H. Cardinality of G is the number of elements in G. These are just positive integers. This number divides. Cardinality of H divides cardinality of G. And we usually write this as with absolute value signs. So H with absolute value signs is the cardinality of H with the number of elements in H, and this is the number of elements in G. So cardinality of H divides the cardinality of G, and the quotient, right? If one number divides another, the quotient's a positive integer, is the number of left cosets of H in G. And the proof is the following. So what is the proof? We proved two things already. Cosets are pairwise disjoint. They're either equal or they have no elements in common. Every left coset has the same number of elements. And The group G is the union of its left cosets. So here's our picture. This is G, and we can partition it into left cosets. A1H, A2H, A3H, up to A sub KH. So these are non-empty sets, so there can only be finitely many of them because G is a finite set. And every element is in one of these cosets. So G is the union, A sub I H. I goes from 1 to K. So the number of elements in G is the sum, I goes from 1 to K, of the number of elements in each of these cosets. But these cosets have the same number of elements. This is summation I goes from 1 to K, and one of the cosets contains the identity. It's just the order cardinality of the subgroup H. So I'm adding this to itself K times. This is K times H. So what does this say? The number of elements in G is some multiple of the number of elements in H. Therefore, H divides G. And K is the number of cosets. It's cardinality of G over cardinality of H. So the number of left cosets is cardinality of G over cardinality of H. Okay? This is Lagrange's theorem. So if nothing else in this course on group theory, nothing else, you have to understand the proof of this theorem and everything that goes into it. Okay. Now, I think I announced on Monday, but let me just repeat. I want to have a second or little midterm exam, which is to encourage you to study some group theory, and it's going to be on roughly 2 weeks. Monday, May 1st, 9 o'clock on campus in Gillette Hall. I think it's in room 205. And it's going to be a short exam, and I'm going to ask you just to prove a few things, including Lagrange's theorem. To see how well you're understanding this, and it gives us a couple of weeks before the final to review stuff if it's necessary. Okay. All right, so we did a lot today, which is good, and there's a lot to learn. And I encourage you to study this. I'll post some office hours for today, tomorrow, and Friday, so you have a chance to log on and ask questions if you like. And we'll see how it goes. Any questions before we stop? Okay. Enjoy the day. Learn algebra. Bye all.
Professor,
Yes.
are you gonna do a review for this exam?
Yes. Yeah, I'll send out a review.
Okay.
I'll try and have it so you have it over the weekend.
Okay.
Okay. Other questions? All right. Bye all.